Hello everyone, today we're going to be talking about something that surprisingly does not seem to have much coverage at all on YouTube. That's the pursuit curve, which is basically a curve that results from the path traced by one object as it chases another. A common example of this is some sort of predator chasing its prey, a fox and a rabbit, a cat and mouse, leopard, gazelle, whatever, it doesn't matter. All it involves is that you have one object moving, in this case in a straight line, and the other object is chasing it. So what this effectively looks like is we have our first object, we'll call this object A, that's the prey, rabbit, whatever. In this case it moves in a straight line. And we have its predator that starts somewhere. We're just going to let it start here, it doesn't matter, it's just arbitrary. And at any moment it goes at the same speed as the prey, directly in the direction of it, moving directly towards it. So in one case it's going here, after a little time passes. Now the prey is up here, the arrow represents the direction it's moving in case that wasn't clear. And it'll keep going like that, and ultimately the sort of image this creates, the curve, it looks like if this is what the prey is doing, the predator will look like it's doing something like this. Now you see it's getting asymptotically closer to this line, and in general, in the case I described, it can never actually reach the prey unless it starts directly above it or on top of it. That's only in this particular case. If it were going faster, or we had different parameters, that wouldn't necessarily be true. But we can analyze that as a function, and we can actually get that into a function y of x that gives us the curve traced by the predator. Now for this you're going to need some understanding of calculus. You need to understand derivatives, integrals, a bit of differential equations, just basic understanding of what it means, and also understand hyperbolic functions. So what we basically have is we have the prey, we'll just call this object A. It moves in a straight line at a constant speed, we'll say v. So if it starts at 0, 0, its position at any given time t is going to be 0t, if it's moving straight up. So that gives us a pretty easy equation for object A. Object B starts at some position, we'll just call it CD, and is constantly moving towards A at the same speed v. So this, what we're trying to find, is some equation that represents the movement of B. To start, we are going to get its derivatives of motion with respect to t for x and y. Basically its vertical speed and its horizontal speed. We know what its total speed is, that's v, which is the same as the speed of object A, but we want to find how much of that is going into the horizontal and how much is going into vertical. So whatever direction it's going to be facing object A. So we can represent this as, so we can get this as a slope. It's just, rise over run, ay minus by over ax minus bx. And we already have something that models the position of A, so 0 minus bx works for the denominator, the numerator t minus by. And from here I'm going to actually change the variable slightly. I'll rewrite that soon. Let x be the horizontal position of B, y the vertical position of B. So slope, I'll say slope of line tangent to the path of B at time t is t minus vt, technically. I should specify now that for simplification, v, what the actual value, doesn't matter, so we'll let v equals 1 to simplify it. It can just be scaled, it's not going to make a difference to the actual function. is going to be t minus y over negative x, and we'll put that negative at the front, y minus t over x. Alright, now we can actually get an angle of that. Angle theta made by B's motion is going to be the arctangent of y minus t over x. We're just going to keep this in mind. We're not going to have to deal with data theta directly because of this definition. So it's horizontal speed, which is also going to be dx dt, is going to be equal to v, which we already agreed is 1, so we can leave that out, times the cosine of the arctangent of y minus t over x. And with a bit of simplification, we can find that this can be simplified to 1 over square root of 1 plus y minus t over x squared. Sorry about that. Alright, this is what we get for the horizontal speed, and in fact what we can do is we can multiply each side of this numerator and denominator by x as such, and if we distribute this x into the radical, x squared, and now we can take out that x. So this is what we have now, and we're going to want the vertical speed as well. It's dy dt, and it's going to be the sine of the arctangent of y minus t over x, and that is going to give us, we can do the same sort of simplification to see where this comes from. I'm not going to, for simplicity's sake. Now, because we are actually going back, if we're basically balancing out the difference in x, so we want to approach 0 in the x direction, this actually has to be a negative. Just sort of a quirk of these functions. But now we have dx dt and dy dt. Now, if we're going to want to find f of x, which is y with respect to x, we can find dy dx equals dy dt divided by dx dt. dt dx is equal to 1 over dx dt, which is going to be negative square roots of x squared plus, I'm going to just reverse the order in there, it's in a square so it doesn't exactly matter, divided by x. This gives us dt dx, so now we can go back to dy dx. Now we already have our dy dx, dy dt defined, that's this. We'll multiply it by our dt dx, which is essentially dividing by dx dt, and they both have the same root x squared plus t minus y squared. Y minus t squared is equal to t minus y squared, of course. Denominator here, numerator here, they're going to cancel out, so we effectively get, and the negative will switch the order of this, y minus t over x. That is our dy dx. Now what we're going to want to do actually is we still have y, t, and x. We don't exactly want that, so we're actually going to get the second derivative of y with respect to x. Let's write that down here. So we're going to derive this, and the thing is, x is the only thing we can actually treat as x. Y and t we're essentially having to treat as functions of x. Keep that in mind. So this is quotient rule, so it's going to give us the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator divided by the denominator squared. It's x times dy dx minus dt dx minus y minus t times the derivative of x, which is 1, and all of this divided by x squared. This is what we get for our second derivative. We have dy dx, dt dx, yt, and x. That's a little unruly. Doesn't seem there's much we can do with that. We can, however, simplify. This effectively turns out to be the same thing as dy over x dx minus dt over x dx minus y minus t over x times 1 over x. Now what I've done here is rewrite this to dy dx. So this effectively becomes dy over x dx. And we have a dy over x dx here. So this is nothing more than negative dt over x dx. The second derivative of y with respect to x is the negative derivative of dt with respect to x divided by x. Now we can just figure out, we already have dt dx, it's up here. Now they both have negatives, so they cancel out, but other than that, we'll get this, but there's a divided by x here, so we're going to have x squared. First we're going to reduce it to just x by multiplying the second derivative by, well, multiplying both sides by x. So I'll rewrite the equation now. X times d squared y over dx squared equals this. And now what I can do is get rid of the x and divide both of these terms by x, so x squared by x squared, so x squared over x squared, well that's just 1. And t minus y squared over x squared is going to be t minus y over x squared, but look at that, t minus y over x, we're squaring it, and that's equivalent to y minus t over x, but what do you know? That's our dy dx. So this is actually just dy dx. So it's a square root of 1 plus dy dx squared equals x times the second derivative of y with respect to x. We'll do a little substitution here. We're going to let u equals dy dx. So therefore d squared y dx squared is u prime. And now we have, quite simply, more manageably, x times u prime equals the square roots of 1 plus u squared. I'm going to write u prime as du dx, and now we can actually just treat this as a plain old differential equation with separation of variables. We're going to divide each side by root 1 plus u squared, and also divide each side by x and multiply each side by dx. So just basic algebra we're going to get. Alright, this looks pretty simple. We're going to integrate each side. Now the thing is, over here we have du over root 1 plus u squared. How do we integrate that? We can use some hyperbolic substitution. We're going to use the substitution u equals the hyperbolic sign of w. And that means that du is going to be the hyperbolic cosine of w. Now in case you don't know, I'm just going to define what the hyperbolic sign and cosine are. You can just take my word that the derivative of the hyperbolic sign is hyperbolic cosine, but this is just, I will use z. This is just to show what it actually means. It doesn't actually affect something. So e to the z minus e to the negative z over 2. And the hyperbolic cosine is e to the z plus e to the negative z over 2. One more identity is useful to know regarding these two hyperbolic functions is that the hyperbolic cosine squared is equal to 1 plus the hyperbolic sine squared. And it's going to be useful, so this equation becomes hyperbolic cosine w dw over the square root of 1 plus hyperbolic sine of w squared. And that is equal to cosine of w dw over hyperbolic cosine of w, which is obviously equal to dw just by itself. And we know that that's equal to dx over x. So we can integrate both of these sides pretty easily. We're going to be using this representation of this because it's a lot easier to integrate. So we integrate each side to get w equals log of x plus g. G will be our integration constant. Now we have w defined up here. U is the hyperbolic sine of w. That means w is the inverse hyperbolic sine of u. So now if we want to get u, we can just take the hyperbolic sine of each side. U equals the hyperbolic sine of x plus g. And this is, as I wrote the hyperbolic sine up here, e to the log x plus g minus e to the negative log x minus g over 2. That gives us u, but u, as we defined earlier, is equal to dy dx. We have that definition up here. We're going to plug it back in, and we have representation of dy dx, and we also have a way of simplifying what we have here. We should know that e to the log x equals x. E to the a plus b equals e to the a times e to the b. So putting these two together, we can get dy dx equals 1/2 times e to the g, and we're going to introduce a constant h. Allow me to define it just up here. H equals e to the g. This is just a constant. It's effectively a constant of integration. H e to the log x, which is going to come out to be x, minus, so e to the negative log x, that's basically 1 over hx. For simplicity's sake, when we're integrating this, which we're going to have to do to get y of x, I'm going to write this as two separate terms, hx over 2 minus 1 over 2hx. Now we can simply integrate each side to get y of x, which is what we've been trying to get this entire time. The big moment. The big moment. That's the integral of hx dx, and 1/2 is a constant, so we can simply factor that out, minus the integral, minus 1/2 I should say, the integral of dx over hx. H is also a constant, so we can actually factor that out. I should have done that earlier. Eluded me. Both of these are pretty straightforward integrals. That's going to give us, the first one integrates to h x squared over 4. This is our function. This gives us a function y of x that describes the curve of the pursuit curve as one object chases another that's going in a straight line, and they're going at equal speeds. This is that function that we have been chasing this entire time. Now, if we wanted to find what the values of h and k are, we'll have to plug in. So we just figured out what the function y of x is that describes the curve that is the path taken by the pursuing object, and now we're going to get a little bit of validation. We already saw in the last section a sort of rough sketch of what it looks like. So we're going to use Wolfram Alpha to plot what it actually is going to look like. And we're going to define these constants are. We're going to play around with it a little and see what we get. We'll start with h equals 1, k equals 0. And as you can see, the curve it plots pretty accurately fits the sketch that we made. And if you imagine something's running along this central y-axis and something's over here chasing it, that makes sense. It's going to be like this whenever the object is lower than where it already is, and once it's higher, which will eventually happen, it'll sort of turn around, start chasing it up like this. So if I make k 10, as it's plotting now, so here we have the plot where k instead of 0 is 10, and we see that changes the curve somewhat. It still looks like it could be a pursuit curve. We're going to actually just keep k as 0 for now, and we're going to change h from 1 to, we'll try 4. So here the curve seems to have gotten kind of flatter, more squished horizontally, so it's more vertically oriented. And if we increase h all the way up to, let's say, 15, now it's actually much higher up. You see here it has to change the scale and everything, because whereas before it only went up to about 2 or 3 up here, now it's at 18, and the shape of it still looks similar to what it was when we were dealing with h equals 1. Now we'll make h something that's rather small, like 1/100th. And you see we get this kind of flattened out thing. It's not that easy to see because of the scale, but this only goes up to 0.012 as opposed to, like, over here we have something that already looks zoomed out from our original curve, and the scale is zoomed in. Vertically, not horizontally though. So this gets sort of stretched out horizontally as we increase h.